the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
Good evening, everyone. Okay.
Evening.
We're good to go? Okay.
Yep.
So like Joe said, thank you for the intro. I'm Rachel. Thanks for having me. I'm really sorry, but I picked up a little bit of a cough, so I do have a bit of a sore throat. My voice is not as reliable as it normally is, so I hope you'll bear with me. I have a mug of hot tea next to me, so that should help. So today, the topic I'll be sharing on is Groundwater 101, and we'll be diving into potable water infrastructure specific to New Jersey. And if any questions arise, please feel free to stop me as you need.
Yeah, we typically do a Q&A right after you are done.
Okay, yeah. That's great too. Okay. So just a little bit about myself. I went to Cornell, where I got my BS in civil and environmental engineering with minors in engineering management and architecture. Like Joe mentioned, I actually did start off as an architecture major. That's what this like little dragon on the bottom of the screen is. The freshman architects build a dragon and then like march it down the main road through campus the Friday before spring break. And then we brought it to the arts quad where we set it on fire and like danced around it. This included the architecture upperclassmen who are usually wearing weird little costumes that they make. And then the engineers retaliate by building a phoenix to battle the dragon. And this all originates back to the early 1900s when there was a student who thought that there should be a College of Architecture day, and he led the students around campus with a model dragon, and the lore was that it was partly inspired by St. Patrick driving the snakes out of Ireland, and this is still an active tradition on campus. It happened earlier this year in March, and I'm sure they'll do it again next semester. I don't think they set the dragon on fire anymore, probably because of safety stuff. Pretty weird tradition. But like Joe mentioned, it turns out architecture really wasn't for me, and I ended up transferring to the engineering school my sophomore year. So throughout college, I interned with a geotechnical contracting firm called Moretrench, and I ultimately went to work there full-time after graduating. I was with that firm for about 12 years, working in deep foundations, ground improvement, and construction dewatering design. So most of the photos on this slide are actually from that era. This cow up here in the top left is from when I was working on a ground freezing project in North Dakota. And then this like alligator below it is from an Army Corps culvert repair chemical grout program in West Palm Beach, Florida. And then the photo directly below that one is from a vibratory stone column ground improvement project for a power plant in Kentucky. This photo up at the top with all of the concrete and rebar everywhere. I'm pretty sure it's from the World Trade Center where we did a bunch of dewatering systems. And then the construction dewatering aspect is where I developed most of the hydrogeological expertise that I have now. Most of my job involved looking at soil boring logs and reading geotechnical baseline reports just like day in and day out. And then after I resigned from that position, I took some time off to travel and hang out. And that was a nice little break. I wasn't really sure what I wanted to do next, to be honest. But I knew that I wanted to pivot from construction. So I was just kind of casually exploring what job opportunities existed just in general. And that's when I was recruited by H2M to interview with their water resources department because of my hydrogeo background. So I've been here for almost 6 years now, working mostly on potable water wells and their associated infrastructure. I had no idea that my, temporary construction dewatering experience would end up lending itself to the drinking water industry, but here we are. So the photo on the right is the only kind of current photo. It's actually pretty recent. It's from a potable water well installation for the South Huntington Water District in Long Island from last summer. So just a little bit more about H2M. It's an architecture and engineering consulting firm. Like Joe mentioned, I work in our Parsippany office. The water resources team in our office is now almost 20 people at this point, which is pretty exciting because when I started in 2020, there were only 6 of us. We're full services, so we offer everything that you need to design a structure because we have many different expertise in-house that can help with everything from land use constraints and permitting, HVAC systems, plumbing for a building. We have structural engineers, electrical engineers. We do drinking water and wastewater. We have surveyors, landscape architects. We have environmental teams and then forensic teams that evaluate structures for asbestos or do like fire investigations. We have construction inspectors who we deploy once projects are actually in the construction stages. And it's great for me because I get to learn a lot from these various departments, but then conveniently I can pass off all of the tasks that I don't have the skill set to be able to perform. So this is just a quick outline of what I would like to discuss today. Just a few things. New Jersey is the most densely populated state in the US. About half of our population relies on groundwater as its potable water source. And we face many of the same infrastructure challenges as the rest of the country. So things like aging pipes, lead, emerging contaminants like PFAS, which we'll dig a bit more into in some later slides. Climate change is also intensifying risk to water systems. Things like drought, sea level rise, leading to increased saltwater intrusion and flooding are pretty big concerns. So we'll go through some hydrogeologic basics, touch on general components of potable water infrastructure, and then hopefully we can like dive back into the topics that make this presentation relevant to the theme of sustainability and the reason why we're all here today. So I'm sure you're all familiar with the water cycle. I feel like this general concept is introduced to us all in grammar school, but we'll dive a little bit deeper without getting too cerebral unless there's interest, I guess. But the basic concepts are extraction and recharge. So we in civilization use wells and surface water as sources of water. Animals also drink from surface sources. Plants absorb water from the ground. And then, those are all kind of extraction points. And then for recharge, the primary source is typically precipitation. And then as water precipitates, it'll fill surface water bodies, percolate through the ground, and replenish aquifers. What's an aquifer? An aquifer is just a naturally occurring underground layer of saturated permeable material. Permeability refers to a soil formation's ability to transmit water. So coarse sand and gravel aquifers tend to store and move the most water. Bedrock aquifers rely on fractures to transmit water and can be productive, but they do tend to have less capacity as compared to sand and gravel. Aquifers, like I mentioned, are typically recharged via nearby water bodies and precipitation. They can be referred to as water table aquifers. That's where the surface of the aquifer experiences atmospheric pressure. They can also be confined aquifers, which means they're bounded by impermeable layers above and below. Sometimes confined aquifers are under pressure, and these are referred to as artesian aquifers. So you can poke a well into an artesian aquifer, and the water level that you'll read in your piezometer will be higher than the upper bounding confining layer. And in some cases, if the pressure in the layer is high enough, water will actually come like overfill your well and come spilling out the top of your well, which is always pretty interesting. You might have to put a cap on your well or build it high enough to meet whatever hydraulic head is in the aquifer. And then aquifers can also be semi-confined or leaky, where it's a combination of it being a water table aquifer and confined. There might be little holes in the confining layers. New Jersey has both sand and gravel aquifers as well as bedrock aquifers. The map on the right kind of shows the general geology of the state. Coastal plain aquifers are sand and gravel. That's like the big yellow zone that's shown for South Jersey. And some examples that we have listed in the key are the PRM, that's the Potomac, Raritan, Magathie, and the Kirkwood Cohansey. Full disclosure, I don't actually have a true geology background, so I can't explain too much about the nomenclature or how you would differentiate one aquifer from the other than their general geologic makeup. But it typically depends on age and how the aquifer might have been formed. So maybe there was a glacial divide or a glacial collision or deposits. There might have been like an earthquake, something that mixed everything up, or there used to be a river somewhere and there's like a valley and it's filled in, or there was never a river, but now there is some water flow. Like very interesting because geology is constantly changing, but it also is very consistent and reliable too. I find it pretty interesting, particularly when my colleague Karen, who is a professional geologist, talks about doing things like fracture trace analyses, or how she used to look at old lineament maps to evaluate the potential for productive bedrock fractures in an area. I don't have any of that kind of educational background, which is why I was mostly stuck looking at soil boring logs, because I need that explicit data to make my assessments, but learning more as we're exploring more systems in New Jersey. So fractured bedrock aquifers are more commonly found in northern New Jersey. You can kind of see like all the different colors towards the top of the map on the right, where we're closer to the Appalachian Mountain Range. And it's typically referred to as the New Jersey Highlands because it's generally the higher elevation area of the state. And then, like I mentioned before, South Jersey is all basically just sand and gravel, and you're very close to sea level down there. These different types of aquifers have different storage characteristics and different vulnerabilities. For example, shallower aquifers are going to be more susceptible to surface contamination. And then deeper aquifers may experience a slower recharge because it takes longer for precipitation to make its way from surface all the way down to depth. Land use also has a critical effect on recharge. Impermeable surfaces make it challenging for precipitation to recharge back into the aquifer. So where you have more development, there's less recharge. It's impermeable surfaces, and you have storm sewers collecting runoff, and that gets sent elsewhere. So storm sewers are typically sending runoff to discharge points that are outside the original watershed that should be getting recharged by precipitation that's hitting an area. And then areas without planting or forest cover also lose a lot more water to evaporation. So for example, I would like think of, kind of wealthy neighborhoods where each parcel is kind of humongous and there's just like a singular little McMansion in the middle, and then the rest of the parcel and the property is just a giant lawn. the precipitation hitting those areas is recharging the area that the water is being extracted from, but it's evaporating a lot more quickly. For me, I think lawns are one of the worst things to have happen to the environment. So these are just a few concepts to consider while we continue discussing the basics of groundwater. Hydraulic gradient is essentially the slope of water table or potentiometric surface. That's the graphic down here on the bottom left. It's the change in hydraulic head over distance. So when slope is non-zero, that indicates that water is moving. And that's almost always the case. There's almost always moving groundwater below us at all times. Next, there's aquifer storage, which is related to pore space. A high porosity aquifer has more potential storage. So if you think about coarser, looser soil layers with larger pore space between each granule, because that's increased volume for water to occupy. If you have very dense soils that are differently graded, so you have small grains filling in the space between big grains, you'll have less room for water to be moving freely through that pore space. And then one formula for you guys in this presentation, Darcy's law, Q equals KIA. Darcy's law describes the rate of fluid flowing through a porous medium. So it states that flow is directly proportional to hydraulic gradient, which is the first bullet. Q is going to be the volume of fluid passing through this porous medium per unit time. And then K is your hydraulic conductivity or permeability, which I had a parameter I mentioned before. This is the property that describes a material's ability to transmit fluids, and it's going to have the same units as velocity, so length over time. And then hydraulic gradient, which we just discussed, the change in head over a given distance, and that's going to have units of length over length. And then A is cross-sectional area of the media that the fluid is passing through, so the zone that you're analyzing. Sorry, I almost skipped the last bullet. So safe yield and overpumping. Safe yield is referring to the rate of extraction of water and having it remain below the threshold of the rate of recharge. So you want your Q in, your recharge, to always be greater than your Q out, your extraction, and then with enough buffer that you're not abusing your aquifer. So if your Q out well exceeds your Q in, that's when you're in overpumping territory. So these are all parameters that we evaluate when we're designing potable water sources to make sure that the well design is suited appropriately for the geology in which you're installing these wells. Okay, so drinking water infrastructure. Typically, we break it down into these 4 components. We're mainly talking about groundwater today because that is my area of expertise, but surface water is also a primary source in New Jersey. Like I mentioned before, 50% of the population of New Jersey relies on groundwater as its source. The other half relies on surface water. Depending on water quality, there will be a level of treatment that's needed. Typically, at a minimum, we implement disinfection. That's usually done with chlorine. We have one client that still uses gaseous chlorine. Very interesting to me because it's so incredibly dangerous, but it's actually one of the most efficient ways to chlorinate and disinfect your water. You can also do UV disinfection. There's a few different methods. And then there are several different accepted, pre-approved treatment technologies on the market for a variety of contaminants that might be affecting your source water. Third bullet, storage. Storage can be pre and post treatment. So you can store your raw water or you can store your treated water. And then the last bullet, distribution, is just how we would get it into our taps via distribution mains and then service pipes. In New Jersey, we have a mix of both public and private water systems. So public systems are managed by government and public authorities or even private companies, whereas private water is referring to water that's managed by the homeowner or property owner. Public water systems are regulated by both the EPA and the New Jersey Department of Environmental Protection, or the NJDEP. A homeowner well does not have the same safety regulations, testing, or treatment requirements as a public water system. And the EPA has created 3 categories of public water system. The first would be the community water system, which you can abbreviate CWS. This would be a public water system that supplies water to the same population all year. So that's your home water utility. It's your main water source. The next one, I'm gonna like get these acronyms all mixed up, but is NTNCWS, and that's gonna be your non-transient, non-community water system. So that's a public water system that by definition regularly supplies water to at least 25 of the same people at least 6 months per year. So an example of that would be a school or a hospital or an office building that manages and operates their own dedicated water system. So as an employee, you might be going into an office and using that water source for 8 hours of the day. And then you don't go on weekends. So that's why they have that duration qualifier of the 6 months per year. And then the last category is your TNCWS, and the TN stands for transient non-community water system. So that's a public water system that provides water in places like a campground or a gas station or a public park. So the population using the source is not consistent, and then the duration is also truncated. So you'll have different compliance requirements for each of these systems, the most stringent being for the public community water system, and the least stringent being for the transient non-community water system, because for chronic exposures, you need to have more stringent regulations. And then if you're just drinking from a water fountain at a public park one time in a year, the water quality of that water is not going to be as critical to public health as your home system would be. And then within the public systems themselves, there are government managed systems, which are not-for-profit entities accountable to the public. And they're often much cheaper if they offer way lower rates, because there's a level of democratic control and transparency for government managed systems. On the other hand, there's also private water companies, which are for-profit corporations, and they're accountable to shareholders, and that generally results in higher rates for customers. And privatization of water can reduce public oversight. I'm not a fan of private water, even though they do make up some of our clientele, but it is becoming more and more prevalent because of just funding and practicality. A lot of smaller municipalities may struggle under all of the growing regulatory requirements, particularly as technology improves and we're all, as a society, creating new contaminants, and then we have to figure out how to get those out of our water. And we're gaining just like a better understanding of everything in our water that we weren't able to test for before. We have new technologies that can test for these things. We're finding out about health effects of different exposures of contaminants we used to not understand before. And health authorities are beginning to regulate more and more treatment requirements to deem our water safe for public consumption. So these graphics are just showing what a typical well might look like. I don't know if you guys have ever seen like a modern water well. You might be thinking of like the old-timey structure that's like stones arranged in a circle, and you send like a bucket down and like lift it up. We have much more modern technology now for installing wells. But basically it's still the same concept. You just have a hole in the ground with some amount of structure, whether it's steel or plastic or concrete. And that's just to prevent soil or rock from sloughing in to keep your structure reliable. Bedrock wells don't typically have a screen, but sand and gravel aquifers do, and that's the graphic on the right. So a screen is just a pipe with uniform openings. They can be machine slotted, wire wound, which is when you just have this first graphic, you have like ribs created by straight wires, and then you wrap a wire around it, and then you can adjust the spacing between each wrap. Or louvered screens, that's also a type of screen. So these screens are allowing water to enter, but they'll hold back the surrounding soils from entering the well. And then the well is, instead of using like a bucket that you lower down to lift water in and out of a well, now we have modern day pumps to extract water. The two typical types of pumps that might be used are vertical turbine and submersible. Submersible pumps include the entire motor and pump assembly being lowered into the well. And then the difference with the vertical turbine is that you have to pump in the well, but the motor is up top of the surface. And there's pros and cons to each. And frankly, pumps can be their own topic and own presentation, but I'm also not very mechanically minded. So I'm gonna leave that topic there. And there are a few different methods for drilling a well, and we won't get into like rig types and mud rotary, air rotary, all of that stuff, but I just wanted to mention the general construction process. For a sand and gravel well, typically a contractor will install a test boring to evaluate the soils and then to verify the design. So you might have an idea that there's a good sandy permeable material from somewhere between 80 to 120 feet below grade. You're going to drill this test boring and confirm what that depth actually is so that you can finalize your well geometry and verify your design. So then that's the zone that you would target with this screen material that's on the side. And then around the screen, you typically install a filter material. So that'll be a uniformly graded sand or gravel that's just slightly coarser than that surrounding soil formation. So it's gonna allow water to more efficiently enter the screen zone, but again, holds back soil from actually entering the well. For a bedrock well, the driller will drill a pilot hole until they find a productive fracture. And then from there, they'll over drill the hole and make it wider to meet whatever capacity that they're targeting. For either type of well, in New Jersey, the regulatory rules require the top 50 feet of a well to be cased and grouted. So usually a steel casing and then grout in the annular space between the casing and the borehole. And this is just to prevent cross-contamination from occurring across different formations and to prevent surface water runoff from contaminating the well. So there may also be a situation in which the well is close to a surface water body and you want to make sure that the well is isolated from that surface water body. Wells influenced by surface water are referred to as GWUDI. It's GWUDI. And that stands for groundwater under the direct influence. And under direct influence of what is surface water. The way that you can tell if your well is GWUDI is via a few different parameters, including biologics. Like if your water tests positive for total coliform or giardia or cryptosporidium, you're likely under a GWUDI situation. pH is also a way to measure, and then temperature. So groundwater is pretty reliably almost always somewhere between 50 to 55 degrees Fahrenheit. Surface water obviously gets warmer in summer and colder in winter. So if you see temperature variability in your water well, you might have an issue with GWUDI. And the concern for these sorts of surface contaminations are that you're exposing your source and potentially jeopardizing your aquifer by allowing contaminants in that the aquifer might never would have been exposed to, except that you poked this hole into the ground by building this well. When you are pumping a groundwater well, you are inducing a change in the naturally occurring water table. The amount of change that you're inducing from the static water level to now your new water level, your pumping level, is what we refer to as drawdown. And the cone of depression is a conical volume where, which is like this little shape here, that is caused by the groundwater table being lowered because of pumping. So if there's robust recharge to an area, the amount of depression might be less. If you have less recharge, then you might have a larger depression. And then radius of influence is like this horizontal distance from the well that encompasses the effects of pumping to the point where you no longer see any drawdown. So it's your radius of this cone that you've created by pumping. If you're in an area with a high density of wells, they can actually steal water from each other as the radii overlap. And that's what the graphic on the right is showing. The DEP actually regulates groundwater wells based on the density of wells in an area, as well as the aquifer capacity. They also take into consideration other environmental factors like sensitive habitats for animals, or things like proximity to wetlands, because you don't want to draw down the water so much that you're now negatively affecting the environment. And then if you happen to be a resident with a private well that's maybe on the shallower side, and then you end up surrounded by a bunch of larger municipal wells, the municipal wells might lower the water table enough that your private well runs dry. So whenever new assets are being proposed, the DEP requires extensive analysis and testing to prove that the new well will not negatively impact any existing assets, as well as the aquifer and sensitive habitats that I mentioned before. So oftentimes when we're putting in a new well, we end up having to do a pump test, and then we'll monitor water levels in nearby assets while we're pumping the new asset to test how much impact is actually generated. And then the DEP will look at this data when they're making the judgment for whether or not to permit this new asset. And it's possible that if you are showing a bunch of influence, they might say, you can't install this well at all, or they might say you can install this well, but you can't pump it higher than X GPM. There's also a concern that because you're changing the water level and that's inducing more movement, that you could cause certain contaminants to migrate. So if there's a plume in an area, east of a site, and then you have a well west of a site, and you start pumping on that well aggressively enough, over time, you'll change the water table in the area, and then it might cause that contaminant to migrate. The amount that a contaminant might migrate will be dependent on the properties of the contaminant itself, whether it's miscible in water or soil. There are some contaminants that stick to soil and won't move even if water is moving. And there's other contaminants that move very easily with groundwater changes. There's different rates of degradation. Some contaminants end up consumed by bacteria or other organics. So there's a lot of nuances to it, but something to think about when you're designing water systems. And then good segue into from moving plumes into contamination and emerging issues. There are two main categories when it comes to drinking water contamination, at least from a regulatory standpoint. So primary contaminants are substances with direct negative health impacts and are subject to legally enforceable standards, which we call MCLs, or maximum contaminant levels. that are in place to protect public health. And then secondary contaminants are non-enforceable aesthetic factors like taste and smell and color. And these are, again, non-enforceable guidelines, but this is also the category that will generate the most customer complaints. So it's always in a water purveyor's best interest to address both. So the primary contaminants, they have to legally handle, and then the secondary, they should want to take care of so that they're not getting, angry service calls all the time. So we'll go through the 4 bullets that I have on the slide, starting with PFAS, which is the treatment topic du jour. New Jersey started regulating PFAS a few years ago, and then the EPA announced their regulations just last year. So PFAS, if you haven't heard of them before, it stands for per and polyfluoroalkyl substances. They're also known as forever chemicals because they're very persistent and hard to get rid of. And they encompass a large group of human-made chemicals found in almost everything. It's most associated with non-stick materials like Teflon and a lot of the things that 3M manufactures. They're like water repellent products, but it's also found in food packaging, makeup, firefighting foam. It's a pretty long list if you Google it later. And there are a few approved technologies for treating of PFAS, including adsorptive media like granular activated carbon, very similar to the same stuff that you find in your Brita filter. And then there's also anion exchange media and reverse osmosis. But all of these also generate waste streams that then have to subsequently be addressed, where you have this concentrated PFAS. And it's also interesting because the maximum contaminant levels that the EPA has mandated for a few of the compounds is pretty low. It's 4 parts per trillion. But the concentrations that you typically find in source water are much lower than the exposure you would get from microwaving and eating a Hot Pocket. So, which they haven't regulated, like, the FDA isn't regulating that kind of stuff yet. So it's an interesting debate. Next bullet, nitrates and chlorides. The concentration of nitrates in groundwater and surface water have been steadily increasing just from the usage of fertilizers in the agriculture industry and even home lawn care. If you use Miracle-Gro in your home garden, you're sending a ton of nitrates down into the groundwater below you. Chloride concentrations have also been increasing, and the theory is that it's likely because of all the road salting that we do in winter. And the MCLs for both of these are on the higher side, high enough that most water systems don't currently have to treat, but as we see agriculture industry growing and road salting increasing, that that might change. And the known treatment technologies for getting rid of nitrates and chlorides include reverse osmosis, anion exchange, and distillation, but those are all pretty expensive technologies to implement. Third bullet, lead service lines. I'm sure most people know about the Flint water crisis that all revolved around lead. DEP mandated a 10-year lead service line replacement program a few years ago, and then now the EPA has released a very similar program. You can treat for lead with filtration. I think oxidation and distillation are 2 other technologies as well. But the issue isn't that lead is in your source water. It leaches out from distribution piping as well as your home plumbing. So a water purveyor can't actually control the concentration of lead that's coming out of someone's personal tap by treating the source, which is why the lead service replacement program is national and so widespread and has such a short timeline, because that's the only way to get rid of it. However, water purveyors can manipulate the pH of water as a way to help mitigate leaching of lead from these distribution materials that do have lead in them. And then last bullet, because of climate change, Sea level rise and saltwater intrusion are pretty concerning, particularly for coastal communities. Obviously, living in New Jersey, we have quite a bit of shoreline, and it doesn't help that we're aggressively pumping wells in the vicinity of shoreline that can also move the saltwater interface. There are coastal systems that are beginning to see a rise in chlorides, which is indicative of the change in the location of saltwater interfaces. I actually have a colleague who says that we probably should have been designing desalination plants starting like a decade ago. She thinks that's the next lucrative treatment technology. So maybe that's where we all start investing our money now to become rich later. These are just a few of the many issues that we're facing. New Jersey hasn't started regulating 1,4-dioxane yet, but that's pretty big out on Long Island. And the way that you treat for that is with advanced oxidation, AOP, which requires like UV lights and ammonia and quenching. It's pretty complicated, and that also generates a waste stream. There's all these lucrative treatment technologies that are coming into play, but they're all also generating waste. They're very expensive to implement. Water purveyors have so many responsibilities, and every treatment process that gets added to the treatment chain leads to increased costs for the water purveyor, which then trickle down to the customer also. But obviously, these are all necessary things because it is a matter of public health, and water is life, So tying this back to sustainability and resiliency, there are a few different strategies to helping protect our most precious resource, and I'll share a few of my thoughts. So infrastructure investment is one of the top things, I think. Like any other piece of civil infrastructure, like our roads and bridges, wells also require regular maintenance and upkeep and eventual replacement. Water purveyors need to be monitoring their wells for the static water levels, pumping water levels, pumpage, which is just the volume of water that they're extracting, and evaluating whether the efficiency of a well is declining over time, so that if it is, they can rehabilitate the well to restore its capacity and lengthen its lifespan, and just maintaining the health of their infrastructure. And then they may also be able to make adjustments on how much they're pumping, going back to the concept of safe yield versus overpumping. And then resource planning, again, well capacities need to be established such that they're not overdrawing from the aquifer. And then we as customers can help reduce the need for excess pumpage by decreasing water usage. Again, like harkening back to the stuff that you learned in 3rd grade about how not to waste water. Like nothing irritates me more than an irrigation system, period. I already said it, Americans' love for their lawns is kind of lost on me. But particularly seeing an irrigation system running while it's raining is like infuriating. I feel like that happens in my neighborhood all the time. But cutting back on that kind of stuff, planting lawns with types of grasses that don't need as much water so that you don't have to water them as frequently. Taking shorter showers, obviously, not letting the water run while you're brushing your teeth, using a dishwasher instead of hand washing. There's lots of little things that do add up. And I feel like it's the type of thing where we each feel like maybe our individual contributions are small, but obviously if everyone participates, it can add to significant change. Climate change mitigation. Before, humans covered everything in asphalt. When rain fell, it would replenish the aquifer directly beneath it. And I already touched on this a little, but now stormwater is being collected and then it gets sent to an outfall that might be outside of the watershed that it was originally collected from. So then the amount of recharge to an area might not actually be sufficient to replenish the wells that are located in these areas, which is why stormwater management is so important. Stormwater recharge basins are one solution to this, where you can kind of keep local water local. Flooding can also be a side effect of increased impervious surface. So reducing the amount of impervious surface can be a solution. And this means limiting urban development or implementing permeable asphalt where possible. And then most importantly, protecting our wetlands. It's funny because a few years ago when my sister was house shopping, I would look at Zillow from time to time to kind of try and help her out and just getting curious about what was available out there. And I would see all of these random vacant lots for sale nestled amongst already developed neighborhoods. And these lots would come with blueprints for a house that could be built and it was permitted already. It seemed like a very nice, easy solution for the housing crisis. But then it became very clear to me that these lots were vacant because they're wetlands and they're likely collecting the runoff from the rest of the neighborhood. So I'm just very curious to see how many of these parcels actually got developed, because you're probably ending up with a lot of neighbors that are furious because all of a sudden their basements are now flooding. And it's because they got rid of this vital wetlands that was in their neighborhood that was meant to collect all of that additional runoff. And then last bullet, sustainable practices. Each of these examples that I list kind of just tie back to the 3 bullets above. So there is a governmental regulatory framework in place to monitor water usage as well. In New Jersey, water purveyors need to have what they call a water allocation permit if they are pumping greater than 70 GPM, or the equivalent is 100,000 gallons per day from their system. So the water allocation permit is actually really extensive. The DEP is very strict about allowing water purveyors to extract water from aquifers, and it can take years to receive approval anytime that you're applying for one of these. And then the state will regulate total annual pumpage. You have to report what you're pumping every year. And there might be monthly limits and daily limits, and then even instantaneous limits where the state will say you can't install a pump in a well that can pump higher than whatever cap they decided to put on your well because of what they know about the aquifer. And then there's like a slew of compliance related responsibilities with having a water allocation permit, including water quality sampling. There's things you have to test for on regular intervals. Some things are more often than others. Right now with PFAS being so common, that's, I believe, on like a quarterly cycle. Things like total coliform and fecal coliform, you might have to test for on a monthly rate. And it might depend on your system too. If your system has proven that it's very reliable for not having radionuclides, then you might not have to test except for every 6 years. And if you're a public water system pumping less than the 70 GPM, you don't need a water allocation permit, but you still need what they call a water use registration, and you still report your pumpage because the DEP wants to track exactly how much water that we're extracting from our state's aquifers. And you can actually log on to Drinking Water Watch. That's like a publicly available website, and you can check your water quality of any public water system in the state. So if you know what your water system is, you can go and look it up. Water purveyors also need to have risk and resiliency plans, water conservation plans, standard operating procedure documents. There's a lot of paperwork when it comes to drinking water infrastructure, and so much of it seems very cumbersome and at times unnecessary, but it all just ties back to having checks and balances in place for maintaining this precious resource. The DEP also has water purveyors monitor their pumpage and their usage to quantify any unaccounted for water. So for example, each well is going to have a flow meter on it, so you know exactly how much water is being pumped out of the source. And then all of the customers. So on your home, you probably have a water meter. There's commercial and industrial properties that have water meters. So the water purveyor is calculating how much water usage is being sent to each structure. And then they look at the delta between those two to evaluate how much unaccounted for water that there might be. The The unaccounted for water sometimes exists because of things like non-metered use, like firefighting. But a lot of the times the delta exists because there's leaks in your distribution system or your water meters are inaccurate. So the DEP has requirements for how often you have to calibrate your meters and how much you're documenting all of this data, because the goal is to minimize the waste of water as much as possible. Managed aquifer recharge is a concept used to restore depleted groundwater levels, and then also for you can use it to prevent migration of saltwater intrusion in coastal areas. So recharge activities are conducted to increase water availability and then mitigate the effects of groundwater overexploitation, because we're pumping so much out of the ground. If we're able to add a little bit more in addition to the naturally occurring precipitation, that's probably ideal. So managing natural storage can include seasonal storage of water during times of high availability. So like during the rainy season, in spring and autumn, and then making that available for periods of high demand, like in the summer dry season when people are, filling their swimming pools and watering their lawns and gardens more often. And then, long-term storage or water banking can be a strategic measure for more sustainable management of groundwater resources. And this concept is particularly important in cases where your source water and the usage area don't occupy the same geography. So I'm coming back to that watershed idea again. There is actually quite a...
Rachel, you have 5 minutes.
Okay, sorry. I think I only have one more slide.
Okay.
So there's like the concept of water mining that it occurs even in New Jersey. Like, for example, the Boonton Reservoir that's located between Boonton and Parsippany. That water source supplies Jersey City. So if someone in Jersey City is watering their lawn and that excess is percolating into the aquifer below Jersey City, it's not coming back to the Boonton Reservoir, which it was originally pumped from. So managed aquifer recharge is likely going to be a critical tool in the future of groundwater resource management. And then just tying it back to Hoboken, I was researching, they're doing all the right things: water main replacement, lead service line replacement, leak detection, all that stuff. And then I was reading about a project called Rebuild by Design, which was an initiative by the US Department of Housing and Urban Development, which has designated $230 million to New Jersey for a project that spans Hoboken, Jersey City, and then I think also Weehawken, which is great because Hoboken is notorious for flooding during major rain events, which is what this picture is here on the right. I've also been reading that Hoboken has been installing rain gardens and bioswales and doing street redesigns to address stormwater management. And then I was also reading about a resiliency park where they built like an underground cistern and then also have surface water storage to help manage all of the excess stormwater runoff that is occurring. And then our final slide, what can we actually do as individuals? You can look into learning more about your own watershed. I've been talking about watersheds a lot. You can use GeoWeb. It's an ArcGIS database that the DEP hosts that has a ton of data on it. So you can look up your watershed there. There's also info about contaminated sites and sensitive species habitats and geology and whatnot. And then something that I am pretty passionate about is advocating for equity in water access. Water is a human right. Water equity just means that everyone has access to safe, reliable, and affordable water, regardless of their income or location. We need to identify gaps in equitable infrastructure, and like recognizing that millions of people lack access to clean drinking water just because of aging infrastructure and climate change, and there just not being enough funding in poor communities. So just making sure that we all have that same access, regardless of what our financial positions are. And then maybe someday our infrastructure will be such that we're not using this like high quality, expensively treated potable drinking water for things like irrigation or for fighting fires. Maybe we'll need to explore gray water reuse or stormwater capture, and then even this is kind of a controversial topic, but then beneficial reuse of wastewater. Like maybe we can use that to be filling our toilet tanks instead of using drinking water for our toilets, and thinking that that might be part of the future of water. Yeah. So.
All right. Thank you. That was an excellent presentation.